All right, folks, this is my lecture on Chapter 16 in the Zoomdahl textbook and Chapter 19 in the Brown textbook, which is about thermodynamics, specifically more on enthalpy and entropy and how they interact and how you can use both of them to predict whether a reaction is spontaneous, and especially involving Gibbs free energy, which is something we will learn about later on. But first, more on enthalpy change. Last time we were learning about Hess's law, which says that you can find out the enthalpy change for a reaction not just by measuring it, but you can also kind of cheat and add up other reactions. And if you can add up the reactions to get that reaction, you can add up their enthalpy changes as well. But this takes advantage of the fact that enthalpy is a state function, and state function means that it's okay to use any path to get to the answer. You don't just have to use the one. So somebody was thinking about Hess's law and realized that you can use Hess's law for any reaction if you had enough reactions to work with. And so what they did is they went and they measured the enthalpy changes for every formation reaction that they could think of. So for example, water, the formation of water is the combination of the elements in water. So to form water, it's H2 plus O2. So they measured that one. And to form iron oxide, it's the combination of oxygen and iron. So they measured that one. And they kind of did this for like a whole list of thousands and thousands of chemicals. And in the back of your book, they've got them all listed, your delta H's of formation. And so that's what these are. So delta H, and you see this little F, that's of formation, and then there's also a little degree sign. So let me talk about what that part means. It's an enthalpy of formation is, like I was saying, when you add up when you have the reaction of just the simple combination of elements required to make the chemical that you're interested in. It's important, though, for these tables for everything to be in kind of under standard conditions. And the standard conditions that they set for these reactions that they measured are as follows. And it's important to notice that this is not the same thing as standard temperature and pressure, which is terrible, right? Because standard temperature is 0 degrees Celsius. But standard state, which is what is represented by this little degree sign here, which I really wish it would stop doing that. What's represented by this little degree sign here in your standard enthalpies of formation symbol, delta H sub F superscript degree. The conditions for standard state are as follows, which are, if it's a gas, the pressure of that gas is 1 atmosphere. If you're dealing with a liquid, it's a pure liquid. It doesn't have junk dissolved in it or anything. If you're dealing with a solid, it's a pure solid. Okay. If you're dealing with an aqueous solution, the concentration of the solution is 1 molar. And the temperature for all of these reactions is set to 25 degrees Celsius, which is room temperature. So those are the conditions for standard state that they made sure were the case when they were measuring the enthalpy changes for all of these formation reactions that you can use for Hess's law stuff. Another thing, another thing that's important to know is that because these are standard enthalpy changes, it isn't that they measured all of the enthalpy. They just measured the change. And so what they did is they decided, okay, let's make it easy to compare things because we have to set some sort of scale here. Let's put the enthalpy changes for elements equal to 0. So, which makes sense because how much energy does it take to form 1 mole of oxygen? Well, form it from what? Oxygen. None. So that's kind of the question of for standard enthalpy of formation is how much energy does it take, or do you get to form 1 mole of this thing from its constituent elements? And if it is an element, then well, it didn't take energy to do that. So and what's nice is that instead of making you do a whole bunch of Hess's law flipping and adding and stuff, this formula is a faster formula, which is basically exactly the same thing as Hess's law. And I'll prove that to you in class. We'll do it. We'll do an example that's the Hess's law way, and then do one that's using this summation formula here. So let me talk about what the pieces are in this formula. So what it says is the enthalpy change for a reaction is equal to basically all of the enthalpies, your enthalpy changes for your products, which is your end, minus your enthalpies for your reactants, which is your start. So this is what I was talking about, the end minus start thing. And this makes intuitive sense because, of course, when you're measuring a change of anything, you just subtract the end minus the beginning. So the end is the products, which is the amount of enthalpy present in the products that you've got, minus the amount of enthalpy from the reactants. And again, you've got the enthalpy, these are the enthalpies of formation. So you would go and look up all the numbers in that table in your textbook. And the funky E is a sigma, which is the Greek letter, which means summation. So this means adding up all of the enthalpies of formation for your products. And then the N sub P is the number of moles times that. So if you had 2 moles of a product, you'd have to go 2 times the number from your textbook. And then you add up all of those for those products. And I'll show you one of these sooner rather than later. So that's all of your products minus the sum of the number of moles times the enthalpies of formations of your reactants. So add up all your products, subtract the sum of all of your reactants. That's how you use this formula, which is the easier way to do than with Hess's law. All right, so let's flip over and do the first question from the back of your notes, because I feel like you need to know how to do this, because we're going to have to use similar formulas over here and down here too. Woo. All right, so here we go. Calculate the standard change in enthalpy for the following reaction, known as the thermite reaction, by using standard enthalpies of formation. So what you're going to do is you're going to add up the enthalpies for your products, and then add up the enthalpies for your reactants, and subtract the latter from the former. So the delta H for this reaction is equal to the sum of, let's see, the aluminum oxide. So now I'm going to go to Appendix C in my textbook, which in the Brown textbook is page 1112. And I'm going to look up the enthalpy change for aluminum oxide for its standard enthalpy of formation. Aluminum oxide. There it is. It says that the delta HF for aluminum oxide is equal to negative 1,669.8 kilojoules per mole. Notice that it's kilojoules. That will be important. What that means is that it takes, there is a release of 1,669.8 kilojoules for every mole of aluminum oxide that is made from its constituent elements. And so that reaction is aluminum plus oxygen yields aluminum oxide. And then to balance it, you're going to need 2, and then 3, and then 4. But this is per 1 mole of aluminum oxide, so we actually have to kind of cut this in half so that it's aluminum oxide, 2 aluminums, and 3 halves oxygen yields 1 mole of aluminum oxide. So this reaction has this enthalpy change. That's what the values in the table mean. So for aluminum oxide, we need to add up the negative 1669.8 kilojoules per mole along with whatever enthalpy change you've got for iron. So let's go look at iron. Hello, iron. It's alphabetical. Iron. Solid. Oh, well, look at that. The value is 0, which if you had been paying attention and understood what I was talking about, you would have gotten. Because the question is, how much energy does it take to form a mole of iron from its constituent element, iron? None. So for this first part here, the sum of the products, what we're going to do is we're going to go, there's 1 mole of aluminum oxide, so that's 1 times negative 1669.8, and then this is the sum of, so we need to add on the enthalpy change for iron, which is 2 moles of iron times 0. So that's this part, minus the sum of that for all of the reactants. So that's minus, all right, and let's see, aluminum, 2 aluminums, which let's look for that one. How much energy do you get when you make aluminum out of aluminum? None. So 2 times 0 plus the sum of all of our reactants, iron oxide. So then the question is, how much energy do you get when you make iron oxide? Fe2O3, negative 822.16. So the delta HF, the standard enthalpy of formation for iron oxide, is negative 822.16, which means that Fe2O3 is made from iron and oxygen, and we're going to have to balance that again. It looks like exactly the same way. Yeah, so that means that the enthalpy change for this reaction is negative 822.16. This is an exothermic reaction. So you stick that in there for your sum, and that's, where am I? Here I am. And there's only 1 mole, so 1 times 822.16. So then I stick that in my calculator, and I'll get back to you in a second. Okay, I'm back because I got my calculator. And what thing I just noticed is that there's supposed to be a negative here, in case you were wondering. Negative? Where did the pen go? There we go. That's negative 822.16. I didn't drop that negative for any good reason. And the value that you get with negative 1669.8 minus negative 822.16 is negative 847.64 kilojoules per mole. That is the enthalpy change for this reaction. Bam. All right. Next. All right, more about entropy. So we've been talking about enthalpy and whether a reaction is spontaneous. And what we have learned about enthalpy and spontaneity is that, and this makes sense, is that if a reaction is exothermic, which means that it has energy and it goes out, it has a tendency to be spontaneous, but that's not everything to it, because sometimes you've got endothermic reactions that will go. Exothermicity is one factor in whether or not something is spontaneous. The other factor in whether or not something is spontaneous is entropy. And we talked about entropy and what it was, and also the second law of thermodynamics, and what the relationship that it has to spontaneity is related to the second law of thermodynamics. The second law of thermodynamics says that the entropy of the universe always increases. And so if you've got a reaction that increases the entropy of the universe, then it's definitely spontaneous. But when you break it down into the system versus the surroundings, it gets a little more complicated. So if the entropy, if the reaction causes the entropy of the system to increase, it's more likely to be spontaneous, but you also have to go and examine the surroundings and kind of add them up and stuff. So the two things that we know are, if the enthalpy is exothermic, it's more likely to be spontaneous. And if the entropy increases in the system, it's more likely to be spontaneous. But we haven't quite worked out everything yet. We'll get there when we get here. So entropy is the randomness of a system, and the entropy of the universe always increases. One thing that I wanted to make more clear is this concept of how entropy is related to probability. So let's go over to this picture here. Can we drag this over? Yeah. All right. So this is an image which shows basically you've got this kind of crazy shaped flask here that has a narrow neck and two glass bulbs. And what they're showing is that there are four particles inside this system with the two bulbs. And what they're showing is all of the possibilities for kind of basic location of these particles. So what they're showing is that there is one microstate in which all four particles are in the left bulb. You can have several options where you've got three particles in the left bulb and one particle in the right bulb, which is basically the blue, the yellow, the red, and the purple. One of those could be in the right bulb. So you've got one possibility for everybody on the left, and four possibilities for three on the left and one on the right. When you get it to two on the left and two on the right, you end up with six possibilities, which are the six different pairs of colors that you can have. And then when you've got three on the right and one on the left, it's just the opposite of this one. And when you've got four on the right and none on the left, you've only got, again, one possibility. So what this is showing is that this is unlikely. The most likely state for this system is to have two on the left and two on the right, which is something that we would have guessed, but this is showing kind of mathematically that that is what is most frequent. This is the most common, and this is the least common. So this is very probable. These are pretty probable, and it makes sense to us that it's unlikely for all of the particles to crowd over onto one side. It gets much more true when you're dealing with more than just four particles. And what this is showing is that is kind of the concept of entropy. It is the system proceeds to the most likely case. The most probable thing is what we tend to go towards. So, if you started with your system in this state where you've got four particles on one side, it is unlikely that it will stay that way forever. It is going to proceed towards a more disorganized and randomly assorted setup with two on one side and two on the other. That would be a spontaneous process. So from this state, state 1, to state 3, it is more likely to go forward rather than backward. If you started in one of the states that is state 3, it is pretty unlikely that all four particles would crowd over onto the left side. So the process from state 3 to state 1 is non-spontaneous because the entropy is decreasing when you go to state 1. So that's the relationship between the concept of probability and microstates and entropy, is that if you can kind of understand how likely something is, how many options you've got for a certain state, then you can get an understanding of the spontaneity of the process and the entropy involved. So this section is high entropy, these are low entropy. So there you are. This one. So some rules for looking at reactions and kind of understanding whether the entropy is increasing or decreasing. When you're dealing with a solid, solids are pretty organized. The particles don't have a lot of options for moving around because they're stuck to each other. So you have a relatively low number of microstates. So when you're dealing with a solid, the entropy is relatively low. Comparing that to liquids and solutions, those particles are close together and attracted to each other, but they can slide past, and so they do have more options. There are more microstates available for a liquid or for a solution than there is for a solid. So there's more entropy in a liquid or a solution than there is in a solid. Gases, however, are way less ordered. Gases, the particles can bounce around anywhere, and so there's a much higher entropy associated with gases than there is with liquids or solids. One type of question that you frequently run across is, well, do you think the entropy in this reaction is going to increase or decrease? And the key to that question is basically looking at how much gas there is in the products versus the reactants. If your reaction makes more moles of gas, your entropy is increasing. If your reaction is decreasing the number of moles of gas, your what's my sentence? If your reaction is decreasing the number of moles of gas, then your entropy is decreasing. So that's the key to that question. So think about the solids, liquids, and gases and the number of microstates available to them. Also, large molecules, if you've got complicated molecules like big biological molecules or just a small versus a slightly larger molecule, because in a larger molecule there are microstates associated with rotational motion and vibrational motion of the atoms relative to one another in bonds. The more atoms there are, the more microstates there are for each molecule. So a complex molecule has more entropy than a simple molecule. All right, so we've talked about the first law of thermodynamics, which is that the energy of the universe is constant, but it can change from one form to another. We've talked about the second law, which is that the entropy of the universe always increases. And here's the third law of thermodynamics, which I think is kind of a funny law, which is they've said that if you've got a perfect ionic crystal and you've got that crystal at 0 degrees Kelvin, which we've never actually done, they said that that is just the most perfect, most organized thing ever. And so that is equal to 0 entropy. There is no disorganizedness. There is no entropy associated with a perfect ionic, and ionic because the atoms are rigidly held and can't move at all in an ionic crystal, especially at 0 degrees Kelvin. So they set that equal to 0. Why would you do this? Because again, it's easy to measure changes in entropy. It's sort of hard to measure entropy itself. So they had to set a 0. So you end up looking at delta S's instead of just S's, which, by the way, entropy's variable is S. A big capital S, because this is also a state function. All right, so delta S, and then if you look, you've got a little degree sign. And one of the types of questions that you're going to run across is, well, did the entropy increase or decrease? Because if you remember, it's important to know whether the entropy increased or decreased, because that's going to help us understand whether this reaction is spontaneous. So this formula is exactly the same as this formula down here, except that it's replacing all the H's with S's. So what this is saying is that the change in entropy of a reaction in standard state is equal to the entropies of the products minus the entropies of the reactants. And also on page 1112 of your textbook, they have calculated lists of all of the entropies of each of those compounds that I've mentioned. So that's the third column where you can look up those numbers. So I will go and do one of those questions. So that's question 2 on the back of these notes, instead of waiting until later. One thing to be aware of, in the textbook, the values for the standard enthalpies of formation are in kilojoules per mole. The values for entropy are pretty small, and so they have them in joules, not in kilojoules. So entropy values are in joules per mole, degree Kelvin. And so there's one formula that you've got to use both the enthalpies and the entropies that's coming up in a little bit. And if you're using the values from the book, you've got to convert the entropies to kilojoules, because they just don't match otherwise. So it's sort of a pain, but it's a little tidbit that you've got to remember, or your numbers are going to be ridiculous. So all right, let's go to question 2 on the back of the notes. All right. And all right, the reaction between nitrogen and hydrogen to form ammonia is represented below. Here it is. Nitrogen, hydrogen, ammonia. And the delta H of this is negative 92.2 kilojoules in standard conditions. Predict the sign of the standard entropy change for the reaction and justify your answer. All right, so they're saying this is a really common type of question, and what they're saying is the sign, so is it positive or negative? So is the entropy going to increase or decrease when you're dealing with this reaction? And if you remember, what you're looking at is basically, is there going to be more or less gas? Because gases have got so many more microstates and so many more probabilities that if you've got an increase in the amount of gas, you've got more entropy, and if you've got a decrease in the amount of gas, you've got less entropy. So let's go look. We've got 1 mole of nitrogen gas and 3 moles of hydrogen gas for our reactants. So we've got a total of 4 moles of gas on the reactant side. Those combine to form 2 moles of ammonia gas. And because you're going from 4 to 2 moles of gas, that's going to be a decrease in the amount of gas, which is a decrease by half in the amount of microstates that are possible in this system. So because that's a decrease in microstates, that's a decrease in entropy and disorganizedness, and so we're going to have a negative delta S under standard conditions. So justify my answer, there are fewer moles of gas. All right, use your textbook's table of delta S values to calculate delta S for this reaction. So we've got delta S for the reaction is equal to the sum of the product guys minus the sum of the reactant guys, S's. So delta S of reaction. So let's see, we've got the products, which is going to be ammonia. So let's go to our textbook and find ammonia under the nitrogen section. LMNOP. There we go, ammonia. And we've got a couple of ammonias. We've got aqueous and gaseous. This is gaseous ammonia. And the entropy change the entropy of ammonia, which is, it's being compared to that standard perfect crystal here. The entropy of ammonia gas under standard conditions is 192.5 joules per mole Kelvin. And the entropy of nitrogen, which we're going to need in a minute, is nitrogen gas is 191.5. Now, it's important to notice when you're dealing with enthalpy changes, they've set the elements equal to 0 because the question is how much energy does it take to make an element from its elements? So that answer is obviously 0. These entropies are how much entropy does this have? So don't think that the elements' entropies are 0. Does nitrogen gas have some entropy? Yeah, it does. In fact, this is how much it has under standard conditions. So the enthalpies for elements are 0. The entropies for elements are not 0. The only thing that has an entropy of 0 is that perfect crystal. That's the third law of thermodynamics. Right. And then the entropy of hydrogen gas is, hydrogen is 130.58. Whoa. Okay, so the sum of the products and the sum of the reactants. So the products being ammonia, you've also got to remember that there are 2 moles of ammonia, so that's 2 times 192.5. So that's all of our products, minus all of our reactants, which is 1 times 191.5 for nitrogen, and all of our reactants include 3 times 130.58 for hydrogen. Okay, so that gives us delta S of the reaction to be 2 times 192.5 for our product's entropy, minus the reactant's entropy, which is 191.5 plus 3 times 130.58, which is equal to negative 198.24 joules per mole Kelvin. Now, what's nice is it's negative. We care because we predicted that it would be negative. We said, yeah, I bet it's going to be negative because we've got fewer moles of gas. So we've got a decrease in the amount of entropy. Things are getting more ordered. And so that is what we got. We see that we've got a negative value for our entropy. So the entropy is decreasing. Now, what's interesting is the entropy is decreasing. Well, but doesn't entropy always increase? The entropy of the universe always increases. In this case, this is the entropy just of our system. And so we would need to look at what's happening with the entropy of the surroundings to understand what's going on. We don't really have any data on that right now, but the entropy, if the entropy of this reaction is decreasing and it's spontaneous, we do know that the entropy of the universe is always increasing for spontaneous processes. This is a spontaneous process. And so what's happening is the entropy of our system is decreasing, but the entropy of the surroundings is increasing. So it's kind of tricky when you end up with a decrease in entropy in the system. It's not necessarily a reliable that you know that it is the universe's entropy is increasing. So it's sort of hard. It's interesting that the delta H of this reaction, the enthalpy change, is negative. So this is an exothermic reaction. And so that makes sense to us that an exothermic reaction would be spontaneous because it's easy for a system to lose energy if it's got some. It's hard for a system to gain energy because it has to find it from somewhere. So these two things, which are related to the spontaneity of this reaction are opposed. You've got the enthalpy change, which is favorable, being negative and exothermic, and you've got the entropy change, which is unfavorable. When you consider the system's entropy change, the entropy is going down. So the question is, who wins and why? And we will get to that in our next lecture. So because it's already been half an hour, I am going to do the other half of these notes next time. Bye.